And just so you guys know, I forgot to hit record with my morning class, so I'm going to share this recording with them as well. I was evaluated again this morning, so I think just having evaluators in my class all week put me off my normal, and I forgot. But I am now done with all the evaluations, so until next year. Are we at time? Yeah, you can ask now. Go right ahead. 1B on worksheet 19. Why do we start counting the carbons from the right rather than the left? Okay, let me pull it up. Because I don't know off the top of my head. This is one of the naming ones, though, isn't it? Let's see. On 1B. Okay, so, oh, wait, that's not B. Okay, so you start from the right because the ketone. Sorry, I'm going to share it just to make it a little easier to talk about it. Okay, so on 1B over here, you start numbering it on the right-hand side because that puts the ketone at carbon number 3. If we start on the left-hand side, the ketone will be at carbon number 4. If you have a functional group on your chain, we want the functional group to have the lowest number possible. If there isn't a functional group, like if there's just some carbon substituents and halogens, then we just want the lowest numbers overall. Or if the ketone was like in the middle of the structure, then you, like for letter K, for example, the ketone is going to be on carbon number 1 because that's where you're going to start numbering it. And then whether you go to the left or you go to the right, then you're basing it on the lowest number of substituents. Or I'm sorry, let me rephrase that. Then you're basing it on having the lowest numbers for all your substituents. Does that make sense? Okay, I see your thanks there. Okay, so the ketone function group is correct. Yes. So we talked about naming with like that priority order for that chart. Whichever is, so if there's more than one functional group, whatever's highest on that list becomes part of the parent chain. So whatever becomes part of the parent chain, that takes priority for having the lowest number possible. Yeah, so yeah, exactly. So after the ketone or whatever the functional group is, then you start to look at the other substituents. And a lot of our, well, I shouldn't say a lot, but a handful of our substituents have to be on carbon number 1, like aldehydes, carboxylic acids, esters, amides. So they make it a little bit easier. Okay. So before we dive into lecture today, a couple things I want to mention. I am in the middle of grading exams. It takes a lot longer to grade them digitally than it does if they were on paper. So my goal is to get them to you next week. So to kind of go along with that statement, I am also telling you guys I'm going out of town this weekend. I'm going up to Big Bear to really just quarantine in a different place. But I have no idea what my signal or the Wi-Fi will be like. So if you text me or email me and I don't get back to you for like 3 days, that's why. I'm gonna bring stuff with me. I'm gonna bring my tablet with me, but I don't know what kind of situation we're gonna have. The review said Wi-Fi was spotty, so I might just be unplugged for the weekend, which won't be a horrible thing. So with that being said, though, if there isn't Wi-Fi, I can't grade your tests through Canvas. So we'll see. I think that's it, though. Yeah, I think that's it because we talked about all the other stuff on Monday. So we are going to finish up chapter 19 today. There we go. Let's do this and make my little video smaller. There we go. Okay. So we ended with this slide on Monday, and we had talked about a lot of different oxygen and nitrogen-based nucleophiles. And so where we're picking this back up is actually looking at how to reverse some of these reactions. And so we're looking at the reversal of the not that button, there we go. We're looking at the reversal of the acetal, the imine, and the enamine reactions. And all of them are just using water and an acid catalyst. And then all of these are showing that it's forming a ketone. But if there was a hydrogen right here instead, then it would form an aldehyde. So all of these could form a ketone or an aldehyde. It just kind of depends on what those substituents are that are already attached to that central carbon. We are going to look at the mechanism for that acetal reversal. And it's not going to be on the screen because I don't save the drawings. So it's going to look like a giant blank screen. But on Monday, we talked about the acetal mechanism. So if you go back and look at the video or your notes, you'll have that in there. And so that was slide number 12. And I bring that up because now we're going to do the same thing, but in reverse. And so really the mechanism we're going to look at is going to be all the same steps as what we've already seen in the reverse order. So we're starting with our acetal. And we know we're going to eventually make a ketone. So just based off of that, we know we have to get rid of both of those OR groups. And we know that we need to add on an OH group. So we are in an acidic environment. So we're going to start with a proton transfer. So there we go. We have one of our oxygens is protonated, one of them is not. What do you think is going to happen now? What's going to happen to that protonated oxygen?
It's a good leaving group.
It is a great leaving group. So we're going to kick off that leaving group. The other oxygen is going to form a pi bond. And so we've seen this same thing happen in a couple of our reactions where we lose one of the substituents and the other one just forms a double bond. So now we have that carbonyl. It's not really a traditional carbonyl. It has that R group attached to it still, but it's a carbonyl. So now water gets to come in. And we're going to do a nucleophilic attack. That water is eventually going to become the oxygen for the ketone. So water comes in. We're going to form a lone pair from that pi bond onto the oxygen. So there's our OR group. There's our water molecule. What are we going to do now?
In this stuff, just because that water is there, it makes me think that it's also a good leaving group. Does this go back and forth?
Yeah, this is definitely reversible. And that's one of the reasons why we are able to get it back into the ketone form, just like we could move it into the acetal form. So you're completely right. This is completely reversible. So in the forward direction, though, what would our next step be? Could you quickly go over what makes something a good leaving group? Yes, that is a great question, Nilla. So there's a couple things. So ignoring oxygen for right now, because oxygen by itself is not a good leaving group. What makes a good leaving group is something like a I was thinking chlorine and bromine, and I combined them into just a new element. Yeah, fluorine. So bromine and chlorine are both really good leaving groups because they are stable as ions by themselves. Good leaving groups are weak bases. So this does go all the way back to Ario when we talked about acid, base, and strengths, acid and base strengths. But really it means that it's an ion that is stable by itself. For things that aren't good leaving groups, like an OH is not a good leaving group. So instead, we're going to add a hydrogen to it because now, as a leaving group, it becomes just a water molecule. And so as a neutral water molecule, that is stable and happy. If we broke it off as just an OH group, that's going to be a hydroxide. And a hydroxide is a strong base. So that means that it's going to want to react with something else. But if we have a weak base, like water or bromine or chlorine, they're not going to easily react with other stuff. Does that make sense?
So back to the problem, does either more acid come in and repeat the original process, or does the conjugate base come and strip a hydrogen?
Yes. Both things happen. So I'm going to erase all this. So we normally draw it one at a time, but you're completely right. Those two things are going to happen. And I'm going to draw it as the hydrogen getting removed first.
But it doesn't, they both can happen first. It doesn't particularly matter the order.
Yeah, it doesn't particularly matter. I usually draw it this way first because having two, so if we put the hydrogen on the other side first, that means we'd have two positive charges on the molecule at the same time. And it's just not as likely, not as stable. And so it's probably going to happen on this side first. So we're going to do a proton removal, a deprotonation. And then on the other side, we will protonate. So then we are really just going to repeat the same thing. So the same thing that happened right here, where we lost our leaving group, we created that new pi bond. We're going to do the same thing. We've made another good leaving group. We made an alcohol molecule, so something that's going to be stable on its own. So loss of a leaving group right there, that ROH group leaves. And then we're going to form that new pi bond with our alcohol oxygen. And then last up, we just have to get rid of that hydrogen. So lots of proton transfers, but that's to be expected because we were using a neutral nucleophile and we were in an acidic environment. So we have to add all those hydrogens in and also remove them all as we go through it. So kind of ended up in a spiral shape here, but there's our starting material and our ending material and all of our little mechanism arrows to get there. So it is a lot of small steps, a lot of small things to keep track of. But in that middle part, we talked about that some of that order doesn't matter. That happens in a few of these types of reactions because in reality, some of these things are just kind of happening together. So it's not uncommon. Now, one thing to keep in mind, though, if you kind of have the idea of a mechanism remembered, but maybe not a perfect memory of what's going on, one thing to keep in mind is that the environment you're in. So this is an acidic reaction. We have an acid catalyst. So that means that all of our reagents, all of our transition states, and all of our intermediates should either be neutral or positively charged. We're not going to have something that's negatively charged in an acidic environment. And then the opposite's true. If we are in a basic environment, everything is either going to be neutral or negative because we're in that basic environment. So that's something to keep in mind because, for example, if we're down here in this step and we thought, well, I need to get rid of that OR group, and you lose that OR group, well, now you've just made a negative OR as a leaving group. So that should give you a little flag, a little warning flag to say, oh, that should probably be protonated first. There's acid in this environment. So just kind of keep the environment, whether it's acidic or basic, in mind as you're trying to work out those mechanisms. Or even just something to observe as you're trying to memorize them and learn them, because memorizing them, I understand, is kind of the first step, but understanding those steps and seeing what's happening is going to help you figure out other ones or learn other ones. Because remember, I told you that there's 44 reactions in the next chapter. So you can't memorize all those mechanisms. It's just not, it's not okay. So you have to understand what the steps are and why they're happening. Okay, any other questions about this mechanism? I kind of went off on a little tangent there. Okay, then let's move to some sulfur nucleophiles. Now, what's super nice about the sulfur nucleophiles is this bullet point right here. Sulfur is in the same family, in the same column on the periodic table as oxygen. So that means that they react very similarly. And that means that for this reaction, the mechanism is going to be the exact same as what we saw for the acetal. So the acetal is when we added alcohols. In this reaction, we're going to add thiols. But how it reacts is going to be the exact same. Again, we can start this with a ketone or an aldehyde. Either one will give us the same results. We're going to use an acid catalyst, and we make a thioacetal. We've definitely talked about that prefix thio before, and it might have popped up in your biology classes, but it means sulfur. I'm sure there's some Latin meaning behind it. I don't know what it is off the top of my head, but it does give us an indication that there's sulfur present. And then the one on the bottom is essentially the same thing, but we're making a cyclic thioacetal. And just like with the oxygen, we can use a carbon chain that is one longer than the one in the example. So the one in the example on the bottom has just a 2 carbon chain. So we make a ring that has 5 atoms in it. But we also know that a 6 atom ring is very stable. So let's see. Sulfur. There we go. So we could make it with a 6 atom ring as well if we start with 2 thiols that are separated by 3 carbons. If we have too short of a chain, if there was only 1 carbon in between them, that would force a 4 atom ring to form, and we know that has too high of angle strain. That's not going to be happy. And if we tried to have 4 atoms or larger, the ring size would be 7 atoms or larger, and it doesn't have the right ring or the right bond angles. So as the first sulfur adds and that second sulfur is trying to kind of wrap around, it's not actually hitting in the right spot. So the chain is too long to make the connection. So having 2 carbons or 3 carbons gives us the right length, the right shape and size. We can also take the sulfur groups back off. So reaction number 5 is desulfurization. So we have our cyclic thioacetal, and we are reacting it with Raney nickel. So this is a metal catalyst. And it's going to reduce it all the way down to just the alkane. So this is going to completely get rid of any functional group that's at that position. So this is something that, well, if you're starting with a ketone, it would be a way to completely get rid of that ketone through this cyclic thioacetal pathway. Yeah, that's all. I was going to say something more, but that's pretty much it. I was going to say the same thing again. Any questions about that one? Okay. We're going to look at some carbon and hydrogen based nucleophiles next. And we're starting with hydrogen. And in both of these reactions, we are using what's called a hydride. So we can start with a ketone or an aldehyde. And then our two options for reagents, LAH is lithium aluminum hydride, and NaBH4 is sodium borohydride. And then they both have a hydrogen source. So in the first set of reagents, we're adding water. And then in the second set of reagents, we are adding methanol. They're serving the same purpose, though. They're both going to be a hydrogen source. These look like very different reagents, but we're going to talk about what makes them very similar, makes them react the same. So lithium aluminum hydride, we have a lithium cation. We have an aluminum bonded to 4 hydrogens. And then sodium borohydride, sodium cation, boron bonded to 4 hydrogens. What do boron and aluminum have in common? They can both be Lewis acids. This is true. So how they are acting as Lewis acids in this case, and what they have in common, why they work in the same way here, is the types of bonds they like to form. So first of all, the lithium and sodium, they're not doing anything for us reaction-wise. They're there as cations to balance out that charge, but they're not taking part in the reaction. Aluminum and boron each have 3 valence electrons. So where they're at on the periodic table, so they're right over here. They're right next to carbon, or then they're in the column next to carbon. I should word it that way. They have 3 valence electrons, which means that they want to form 3 bonds. And with those 3 bonds, they're only going to have 6 electrons around them. So they're one of the exceptions to the octet rule. They only want to have 6 electrons, which makes them neutral, makes them happy, but it does mean that they have space to take on extra electrons. So that's why we can use them as Lewis acids. They can be electron acceptors. So if we're thinking of them in that terms, what we're looking at is actually their conjugate bases. They've already taken on those extra electrons. And so when these react, they want to get rid of electrons. And so to get rid of these electrons, they're going to kick off a hydrogen with its electrons. So notice in both of their names, they both have the word hydride. We use the ending "ide" to tell us that something is negatively charged. And yeah, "ide" gets used in other things also, but most commonly it gets used to say that we have a negative charge. So with both of these, we're using a hydrogen with electrons. So down in the mechanism here, in that first step, look at where that bond, look at where the arrow is starting. So it's starting right at that bond, and we're doing our nucleophilic attack So we're starting from the bond between the aluminum and the hydrogen. So this is not a hydrogen transfer. We're not using electrons to reach out and grab onto a hydrogen. The hydrogen is doing the attacking. The hydrogen is bringing its electrons with us. So because of that, that's what makes this a hydride. And then at the same time, those pi electrons become a lone pair on the oxygen. Next step then, we're using the water to do that proton transfer. So we're starting at the lone pair on that oxygen to grab onto that hydrogen. So there's our difference between a proton transfer and a nucleophilic attack using that hydride. It's where that electron source is coming from, where the arrow starts. If we showed this mechanism with the sodium borohydride and the methanol instead, the only difference is over here, instead of the aluminum, it would be a boron. And instead of a hydrogen over here on that water molecule, it would be a methyl group. So the mechanism itself is going to look exactly the same. There's just going to be some slight differences because of the chemicals we're using. One of the other things that the slide tells us about the reaction is that if we do start with an asymmetrical ketone, so it says if it's unsymmetrical, that's referring to the ketone. So if the ketone is asymmetrical, we will get a racemic mixture. What does racemic mean?
Both enantiomers?
Yes, we will get both enantiomers. So down here with our final product, we have the alcohol, we have the hydrogen. So if those two R groups are different, then we will get both the R and the S enantiomers. And racemic specifically means that we will get them in equal amounts. So the equal, here, let's put little concentrations around them. So equal concentration of R and S. And the reason for that, and I might have mentioned this on Monday, I can't quite remember, but the reason for that is when we have our ketone or aldehyde, it's an sp2 hybridized carbon, so it's trigonal planar. So when that hydride approaches, it can approach from the front and we can get one of those enantiomers, or it can approach from the back and we can get the other enantiomer. Because it's flat, both sides are equally accessible. So there's no sterics, there's nothing to worry about. That's why we'll get equal amounts. We haven't talked a whole lot about enantiomers for this because we haven't actually formed a whole lot of stereocenters. So it does come up a couple times in today's lecture, but there's our reasoning why. Questions about these hydride reactions? Okay, then we're going to look at some carbon ones. The first carbon one we're looking at are the Grignard reaction. So number 12, Grignard. And this is what our lab was based on for Monday. A Grignard reagent is some kind of carbon group bonded to a magnesium and a halogen. And that halogen is either going to be chlorine or bromine. When this happens, the carbon actually becomes a carbanion. So let's talk about why. Magnesium is a 2+ cation metal. Halogens, -1. So when we put those together as an MgX, it's a +1. So that's just math. +2 and -1 together give us a +1. We know that. But in order for this to bond with carbon, our carbon is going to have to be a carbanion. So when we show it as a bond between the carbon and the magnesium, that's a little misleading. That's kind of implying that it's a covalent bond, but we have a non-metal, our carbon, bonded to a metal, our magnesium. So in reality, it's really this carbanion and this magnesium halide cation. So when we show the mechanism, we usually show it just as a carbanion. And let's see, well, I'll show you another way to do it once we look at the mechanism. But that's why it becomes negatively charged. That's why it can be a nucleophile. So in the reaction, again, we can start with a ketone or an aldehyde, and we have both shown here. So there's our ketone, here's our aldehyde. We're going to react it with our Grignard reagent. And then in the second step, we're going to react it with some water. Probably didn't need to write the word water. Just got started, kept going. If we start with the ketone, we are going to make a tertiary alcohol. And if we start with the aldehyde, we are going to make a secondary alcohol. And then notice down here, it's going to be racemic. So whatever R group we are adding on, so in this case, the R group is just a methyl, but we have the alcohol, the hydrogen, the carbon group that was already on there, and then our new carbon group. So there's our 4 unique groups. Again, it's flat. That nucleophile can approach from either side. It'll be racemic. The ketone, if it does create a stereocenter, would also be racemic. The example that's shown there has symmetry, so we don't have 4 unique groups. But this one would also be racemic if we create that stereocenter. So let's look at the mechanism down here at the bottom. We're starting with that carbanion, that negatively charged carbon, nucleophilic attack, pi bond becomes a lone pair. Second step, we're adding in that water. Oxygen grabs onto the hydrogen of the water, and then we break that bond. And so we're creating that alcohol group with a new carbon chain. There's one more way to show this mechanism, and I want to show it to you just so that you understand what it means if you see it in the book or on website video or something. So sometimes it will also be drawn with the Grignard reagent with that bond in there. And so for the nucleophilic attack, it would just start at that bond. And so that arrow is showing us that we're forming that new bond between the nucleophile and the carbonyl carbon, but it's also showing us that the bond between the R group and the magnesium is breaking. Both work. You could put either one on the test and I'd be fine with it, but just so you know what that's representing. One of the important things about doing this reaction for real is having the water as a second step. So meaning we aren't mixing all of this stuff together in one beaker at the same time. We're adding in the water, and we're not even adding in the water into our reaction flask. We're actually just adding in the water as part of the workup step. So if we have just some Grignard reagent still in our flask, what's going to happen to it as soon as it hits the water, as soon as it reacts with the water? What are we going to make? So it's not going to react that involved. It's actually just going to steal a hydrogen from the R group. So we're actually just going to make an alkane. It's just going to do a hydrogen transfer. And so we would have the alkane and hydroxide floating around. But another way to look at that or to think about it is that it kills the Grignard reagent. As soon as it touches water, because it transfers a hydrogen onto that carbanion, it is destroying the Grignard reagent. It's no longer reactive. And so when we add the water in that workup step, it's doing a couple things. It's adding the hydrogen to the oxygen, like we saw down in our mechanism in this step here. We do want and need that to happen. Sorry, I'm adjusting electronics here. But the other thing that it's doing is that it is stopping the reaction. So we don't generally add things in an equal 1-to-1 ratio. On paper, yes, they are reacting a 1-to-1 ratio, but we're usually adding something in excess. And when we add the Grignard reagent in excess, we have to react it so that it is no longer reactive. We have to stop it. And so when that water is added in the end, it gives us that proton transfer to create our alcohol, but it's also stopping the Grignard from continuing to react. The word that we use for that is that we say that it quenches the reaction. And so that really is just a chemistry way to say that it's stopping the reaction. It's putting everything to a halt.
So could you describe the reaction as thirsty?
It is thirsty indeed. At least the Grignard is. It reacts so easily and quickly with water that when we do this one in person, you have to dry your glassware in an oven for like 4 hours before you can even use it. And so when we do, this is one that we would normally do in person, but it means that we have to prepare for it like a week ahead of time, because a week ahead of time, I have you wash all the glassware you're going to need for that specific lab. And then because we don't have time to put it in the oven 4 hours before class starts, we just put it in the oven a week before class starts. And so you have to have it all like labeled with Sharpies and everything. But it's the first time I did it, with students, I was not prepared for that. So I think I just went in and dried everybody's glassware for them. But it is, it's an interesting one to do because there's so many little steps you got to keep track of. Any other Grignard questions? Okay, we have a couple practice ones. Fill in some boxes. 1, 2. So we have an aldehyde up at the top. We are going to react it with lithium aluminum hydride and some water, figure out our product. And then on the other side, we are making a secondary alcohol and figuring out the reagents in order to get that product. So let's start on the left. Let's start with box number 1. What is going to, well, let's see. What is our product going to be? So like, what is our functional group going to be when we take our aldehyde and react it with lithium aluminum hydride?
Primary alcohol?
Yeah, exactly. So our aldehyde, our carbonyl on our aldehyde is going to get reduced down to an alcohol. So here's my carbon chain. I still have that aldehyde hydrogen attached. We've added a new hydrogen, and then our carbonyl becomes an alcohol. Now, I know that I did not need to draw both of those hydrogens on there, but sometimes it's helpful to see where everybody came from. So there's our original hydrogen. There's our lithium aluminum hydride hydrogen. What about on the other side? How are we going to make that product? Yeah, I think you guys are both right. So Grignard with a butyl group. So we're going to do some carbon counting because I am 100% sure that butyl's right, but I'm going to show you how to figure that out or double check if you think it is a butyl. So we're going to count how many carbons we have to start with. So 1, 2, 3, 4, 5, 6. And then we look at our product, and this is even something that you should be doing for multi-step synthesis, but even just these one-step problems as well. So if we start counting and we do 1, 2, 3, 4, 5, because it's 5 carbons going to the right, I know that that's not my original chain. It's not the correct length. So I'm going to erase those numbers. So going the other direction, 1, 2, 3, 4, 5, 6. So that tells me that essentially the left side of this molecule is my original chain, and what I need to add onto it is this 1, 2, 3, 4, this butyl group. So my reagents then would be butyl magnesium bromide, or we could draw it 1, 2, 3, 4 bonded to a magnesium bromide. Writing out the way that Nilla did in the chat with the butyl MGBR, all of those would be completely acceptable. All of those work. And then step number 2 is water. Having those as separate steps, 1 and 2, is important. We've talked about why it's important. So if you do leave off the 1 and the 2, that's you're going to lose a point or something on the test because they are separated for a reason. Questions on either one of those? Okay.
Professor?
Yeah.
For the Grignard reagents, is there a steric limitation, or is it usually just a primary that is the best?
So primary is the best because it's a carbanion. We don't talk about carbanions a whole lot, but the carbanion stability is the opposite from a carbocation. So less substituents actually makes it more stable. So we do see things other than primary, but that's why primary is going to work the best. So primary and secondary would be, well, primary is the best, secondary would be okay, and then bigger than that would be less stable. Good question. Okay, on to a cyano addition. So this is still a carbon nucleophile. The carbon is going to be our negatively charged part. And so we're starting with ketone or aldehyde. None of these were specific to just ketone or aldehyde. But I'm still specifying that they can be either one in these. We're reacting this with HCN. So just a reminder, when we have that CN, there's a triple bond between the carbon and the nitrogen. And we're going to make a cyanohydrin. So the name here is pretty nice, pretty descriptive. We have a cyano group. Hydrin. Hydrin is one of the many words we use to say that there's an alcohol. So hydrate, hydrin, hydroxy, they're all referring to that alcohol group that's attached there. I do have a spot here for the mechanism. The mechanism is nice and easy. It follows all the rules that we already know. So HCN is going to break apart in solution because it is an acid. So we're going to get cyanide ions in solution. So we start with a nucleophilic attack, and then those pi electrons become a lone pair. So nucleophilic attack, and then we do have an acidic, or we have the H plus from the HCN. So we can just write it as an H plus, or we could have it coming from an HCN that has not broken apart. So we're going to grab that hydrogen. So proton transfer. And we get our product. So at the beginning of this chapter, when we talked about what 2 steps are going to happen in all of these nucleophilic addition reactions, these were the 2. These were the 2 that had to happen. We had to do a nucleophilic attack to add something to that carbonyl carbon, and then we have to do a proton transfer to make that oxygen neutral. So this is falling right in line with the 2 steps we saw, or 2 steps that are required. Any questions on this reaction? Okay. So last carbon nucleophile, this one is weird. So it's definitely our weirdest mechanism. And it falls under this mechanism heading, a 2+2 cycloaddition. This does not fit the pattern that we've been talking about. So with that being said, this mechanism will not be on the test. I am going to show it to you so you can see what's happening. But because it's not fitting that pattern, you don't really need to know it. It's called a Wittig reaction. And in this reaction, we're creating a carbon-carbon double bond. So it's a really weird reaction, weird mechanism, but it's also a really cool reaction because what it allows us to do. So we're going to start ketone or aldehyde, either one. We're reacting it with this thing. This is called an ylide. And the way that it's drawn right here is that we have charges on the carbon and the phosphorus. So I'm just going to redraw this guy. Because there's actually two different resonance contributors. And I did draw bonds coming off that carbon with nothing on them. I was just trying to make it a little bit more generic. We have it drawn with those charges, but the other resonance contributor, we're just going to move those electrons in between the carbon and the phosphorus. And so we end up with a double bond there between the carbon and the phosphorus. So drawing it either way will work. The carbon with a negative charge, of course, is going to be a very good carbon nucleophile because it's negatively charged. So you might look at the one with the double bond and just kind of wonder, well, why isn't it drawn with the double bond? Wouldn't that make everybody more stable? It would be more stable, but phosphorus is in the next row down on the periodic table compared to carbon, oxygen, nitrogen, our normal atoms we're using. And so because it's on the next row, that means it's larger. And because it's larger, it's not going to have as good of pi bond overlap. So to make that pi bond, we have to use the p orbital from the carbon and the p orbital from the phosphorus. But because they're different sizes, they're just not going to overlap as well. They're not going to be as even. And that means it's just not going to be a very good bond. What are all those little pHs that are bonded to the phosphorus?
Benzene rings.
Yeah, they're benzene rings. They're phenols, yeah. They're there for size, they're there for stability, but they don't actually participate in the reaction itself. And so because that's going to get very bulky to draw out 3 benzene rings every time we have to draw this, writing it out as a pH makes a lot more sense for saving time, saving space. So let's look at the reaction down here to see what's actually going on. We're going to react our ketone with our ylide. The ketone with those 2 R groups is the bottom half of our molecule. We're making an alkene here. And then the ylide is the top half of our molecule. So we're essentially cutting off the oxygen of our ketone. We're cutting off the phosphorus of that ylide, and we are Frankensteining together those 2 pi bonds to make something new. So I actually prefer drawing the ylide with a double bond because the way that I look at it, if I see this and then I have my carbon bonded to those 3 phosphoruses, I'm just going to put an H and a methyl here. The way that I look at this is I think, okay, I'm just going to break it here and break it here, and I'm going to match those 2 double bonds together. So being able to see the double bonds on both starting materials, I think just in my brain, it helps me put those 2 puzzle pieces together a little bit better. A little bit about limitations. The carbon on the ylide can only be monosubstituted, or no substituents. So it can either have two hydrogens like the one in the example down here, or it can have one R group and one hydrogen like the one I drew up at the top. It can't have two R groups attached to it though. Couple reasons. One is sterics, there's just too much in the way. And then the other one, because that is a carbanion, it's going to be more stable when it has less substituents. So we did some limitations. We have to talk about, oh, mechanism first. I was going to say stereoselectivity, but that's on the next slide. I'm just jumping the gun there. So here's the mechanism. Yep, told you don't need to know it, but we are going to talk about it. This first step is that cycloaddition. So right here, there's the nucleophilic attack we are used to seeing. That carbanion is bonding to the carbonyl carbon. The other bond is not something we're used to seeing. Those pi electrons, which normally just go back up onto that oxygen, are bonding to that positively charged phosphorus. So then look at this crazy intermediate. We formed a ring of 4 atoms made up of 2 carbons, an oxygen, and a phosphorus. It's not happy, has a wacky name. It's an oxaphosphatane. Because it's not happy, there's too much angle strain, the atoms are not the same size, they're not the same electronegativity, it's going to break apart fast. So here's how it breaks apart. This arrow going right here is breaking the carbon-oxygen bond and forming an oxygen-phosphorus double bond. So it's making this guy. The other arrow is breaking the carbon-phosphorus double bond and making the carbon-carbon double bond. So that phosphorus-oxygen triphenyl business, that's a side product. It goes into the waste. We don't care about it, but it is being formed. So the alkene is the part that we do care about. So this is showing us what's going on. Let's talk about the stereochemistry then. There's different stereoselectivity rules based on what's attached to our ylid. So this is a stereoselective reaction. That means that both enantiomers can form, but one will be the major product. And if so, in the example here, we're using all the same aldehyde. We're using benzaldehyde for all of these. So really just to have a hydrogen and a larger R group attached so we can easily see sterics. We can see whether it's EZ cis trans, just kind of makes it a little bit easier. In our first ylid, we have a methyl group attached to our ylid and then a hydrogen on the other side. When we have an R group attached, the major product will be the Z isomer. So there's a couple ways to kind of refer to this. When it's saying Z, it means that the 2 larger groups are going to be on the same side. So we can't call it cis because we might not be using an aldehyde. We might be starting with a ketone. So really, we're just thinking the larger side or the larger groups are on the same side. This does have to do with sterics, but this kind of seems like it's going against the steric rules that we normally know. We normally want big things to be apart. I'm going to go back a slide. The reason it has to do with sterics is in this step right here, the 2 carbons are both tetrahedral at this point, and the R groups aren't lined up like they would be in an alkene. They're actually opposites from each other. And so at this point, we want the 2 largest R groups to be as far away from each other as possible. But then as those bonds kind of rotate into place to give us that, that alkene bond, this substituent and this substituent, right now they're as far away from each other as they can be, but as that rotates around to form that double bond, now the big groups will actually be on the same side. So the reason for this is sterics in the transition state, well, how about we put this? Sterics in the mechanism. The other option that's on here is if we have an electron withdrawing group attached to our ylid. So we have a couple examples. We have an ester and we have a benzene ring. So those alkene rings or alkene bonds are electron withdrawing. So if we think about it, we have that carbanion in the middle. The carbanion's electrons can go towards either one of those substituents and participate in resonance. They are pulling those electrons towards them. The rules that we learned in our benzene chapter for electron withdrawers, electron donators, those still apply. Those weren't specific to the benzene chapter. Those stick with us. The rule for this is that our major product will be E. And so that means that the electron withdrawing group and the electron withdrawing group on the ylid and the larger substituent on the carbonyl will be opposites. This has to do with the carbanion stability within that mechanism. So carbanion stability. In order for that electron withdrawing group to participate in resonance, it will be pointed in a direction where it's away from everything else. And so it allows it to have more resonance participation. Both of those reasons for this, I don't think either one of them are even talked about in our textbook. It definitely goes a little bit higher above our class, but I think sometimes knowing the reasoning behind things helps you remember them a little bit better. So carbanion stability within that mechanism and sterics within the mechanism are both our reasons for our stereoselectivity for these reactions. Questions about either one of these rules? Okay, then we're going to practice a couple. Have some boxes. Give some numbers here. So we have a ketone at the top there, and we're going to react it with two different ylids. So I'm even going to put my double bond here just because I prefer the double bond over the charges. Even though I made these examples, changed my mind halfway through. So two different ylids, and then on the bottom we have an alkene, but we are going to figure out how we can make that alkene using a carbonyl and an ylid. So let's start with box number 1. We have a ketone. We're going to react it with an ylid. So I know I'm going to keep that original carbon chain. And I know with an ylid I'm going to make a double bond. So that's the kind of the start of my framework there, the start of my product. At the other end of that double bond, so on that carbon right there, I need to have some stuff attached to it. What should go on the right-hand side? So what should be at the end of that bond?
Hydrogen?
Yeah. And then what's on that side?
The alkane group?
Yeah, so this propyl group right here. So that doesn't look like an alkyne that we're used to drawing. We normally don't draw them in kind of that weird shape. You could definitely kind of unravel that and draw it out in more of a chain format that we're used to seeing. But this works. We can see the ketone that we started with, we can see the ylid that we added to it, and we just kind of combine them together. So it's kind of like when we talked about drawing those bicyclic rings and keeping that hexagon shape and just drawing something else in the middle. It's not the prettiest way to draw them. It's probably not the most accurate in terms of like bond angles, but it gets the point across and it does show us what's being made and we can see the pieces that came together. So the other one is half of it's going to be the same because we're still using that same ketone. So there's my starting point, ketone. Well, what was once a ketone. We're going to have that alkene coming off of that former carbonyl carbon. I'm still going to have two things coming off of there. What am I going to have on the right-hand side this time? So over here.
The carboxylic acid.
Yeah, that carboxylic acid. And then what's on the left-hand side on the bond over here? Okay. So looking at this, we're breaking off that phosphorus triphenyl group. This one is in the Z formation. Our two largest groups are on the same side of that double bond. This one is E, that electron withdrawing group, that carboxylic acid, and the largest group from the ketone are on opposite sides. Questions about either one of those? Does it matter which one is left or right? It does not matter if it's left or right. It matters where it's at in comparison to the other one. So what I mean by that is because I drew the larger side of the ketone on the left for both of these, because I just kept it the same as that original structure, that's what we based the left and the right on. So in box number 1, because the larger group was on the left, that meant that the larger ylid group also had to be on the left so that it could be Z. And then in box number 2, because the larger ketone group was on the left, that meant that the electron withdrawing group, the carboxylic acid, had to be on the opposite side. It had to be on the right side. So when you only have R groups, we want the two large groups on the same side. And when we have an electron withdrawing group, we want the electron withdrawing group and the large R group to be on opposite sides. So when I do these, I usually pick one of the structures to just keep the exact same. So I just kind of redrew the ketone, and then I knew there was going to be two bonds coming off of that alkene carbon, and then I'm looking at, well, what are my two options? So for that first ylid, we had that propyl group, and we have the hydrogen. For the other one, we have a carboxylic acid, and we have a hydrogen. So you know those are the two pieces that you have to put onto the puzzle. And then based off of whether you have R groups or electron withdrawing groups, then you make your decision on to which side they're going to go. Okay. What about this last one? So we know that when we combine a carbonyl and an ylid, we're going to make an alkene. So really, we're just breaking that alkene bond in half. So one of these halves needs to be the carbonyl, and one of these halves need to be the ketone. So I have a 1, 2, 3, 4. I have a butyl chain. Well, I guess they're kind of both butyls, aren't they? I have a 1, 2, 3, 4. I have a butyl chain and then a 5-carbon group, however we want to label that. I guess maybe saying left and right might be better in this scenario. Which half, the left half or the right half, will be the ylid? So there was a rule that we talked about, and I'm going to go back a couple slides. It is the left half. Very good. So I'm going to go back, remind you of our rule, this rule right here. When we have the ylid, we can only have one R group attached to it, and the other one has to be a hydrogen. So when we look at our alkene, the right-hand side has 2 R groups, so that has to be our ketone. The left-hand side with just that butyl chain is going to be our ylid. So I have the phosphorus part of the ylid drawn. I have a phosphorus with 3 phenyl groups attached to it. There's the carbon, and then I'm going to draw the hydrogen on there. So this would be my hydrogen. And then 3 more carbons. 1, 2, 3. And then my carbonyl, I'm going to have a 4-carbon chain and then an extra methyl right there. So kind of like I picture the 2 halves coming together to make our alkene product. When I break this apart, I kind of do the same thing. So I drew that little line in there to show us that we need to break that alkene and have to go backwards. I even just kind of picture, all right, I'm going to put an oxygen right here, and I just created my ketone, and I'm going to put a phosphorus right here. That didn't really look like a P. my pen is too fat, I think. I'm going to put a phosphorus right there on that side, and that half makes my ylid. So just by doing that, we kind of create our ylid, we create our ketone. And this might be something that only helps me, to be honest, but when I took this class, that's how I pictured it in my head, is just kind of inserting in those atoms that need to break that bond. It's obviously not how the mechanism works, but in terms of just moving things around on the paper, it's what made sense. Questions about either one of those? Okay. So we have one reaction left in this chapter. Our last reaction is called the Baeyer-Villiger reaction. Definitely falls into that named reaction category. We are going to start with either a ketone or an aldehyde. So I'm going to draw the aldehyde one out separately. Let's see. We will do it just right here. So ketone or aldehyde, we're reacting it with this, RCO3H. So that's just kind of writing it out in a generic version. Do you remember what that functional group is called, though? We used it in first semester to make epoxides. Do you remember what it's called?
Peroxyacetic acid?
Yeah, it's a peroxy acid. So that peroxy part, a peroxide bond, is when we have an oxygen-oxygen single bond. So like hydrogen peroxide is an oxygen-oxygen single bond with a hydrogen on either side. An oxygen-oxygen bond is not very strong, so that's going to make it more reactive. That's why we use it. So I'm going to label this here as a peroxy acid. One of the very common ones that we use is MCPBA. So this is metachloroperbenzoic acid. So there's some words in there that probably look more familiar now than when you first learned what that meant. I'm going to go this way. So there's the perbenzoic acid, and then metachloro, in the meta position, there's a chlorine. So for the test, for the homework, you will most likely see it written just either as kind of the generic RCO3H version, or MCPBA, because we've seen that in previous chapters. But if you're looking at extra stuff online or watching videos online, they might be using different peroxy acids that you're not used to seeing. But if you see per and acid in the same name, that tells you that it's a peroxy acid. So even if none of the rest of the name makes sense to you, just those two things tells you that it's a peroxy acid. So here's what we're going to make with this reaction. We're reacting our ketone with our peroxy acid. We're going to make an ester. So we're taking one of those peroxy acid oxygens and we're inserting it in between the carbonyl and one of the R groups to create an ester. And if we do this with our aldehyde, MCPBA, we're going to insert that oxygen next to the hydrogen. So we're going to make a carboxylic acid. Regioselectivity. How do we decide where that oxygen goes? What side is it going to go to? If there's a hydrogen, so if there's an aldehyde, it will always go to the hydrogen side. So for for an aldehyde, we will always make a carboxylic acid. It's not going to make an ester. It's not going to go to the R side of our aldehyde. This is because hydrogens are small. So they're easily moved around. So this will make a little bit more sense when we look at the mechanism on the next slide, but it has to do with their size. Now, if you look at the rest of these rankings, tertiary is next in line, a tertiary carbon. What I just said doesn't make sense. Tertiary carbons are not small. And in fact, the rest of the list is in opposite size order. So the reason why we have the rest of the list going from tertiary to secondary to primary to methyl is if we have to move a carbon, what we're moving is a carbon that is in a pseudo carbocation form. So it's going to have a partial positive charge. So this has to do with carbocation stability. So even though it's not a full carbocation, we want something that's going to be as stable as possible. Stability. There we go. So hydrogens, because they're easy to move and they're small. And then after that, we're looking for the carbon group that will be the most stable as that pseudocarbocation when it gets moved. So let's look at this mechanism. Part of this mechanism makes sense. We've seen it before. Part of it's a little crazy. So the first two steps are things we've seen. We're starting with that nucleophilic attack. So here's our peroxy acid. Look at which oxygen is doing the attacking. It is the oxygen on the very end. So I'm going to draw out a peroxy acid here. The carbonyl oxygen and that first oxygen are going to have some resonance between them. They are stabilized together. The oxygen on the end can't really participate in that resonance. So that's going to be the one that's available to form new bonds. It's going to be the one that wants to get out of that structure. So we're going to do a nucleophilic attack and try and trace over this wavy arrow. The pi bond is going to create a lone pair on the oxygen. So our nucleophile is a little bit weird, but that mechanism step is everything we've seen so far. Nucleophilic attack, pi bond becoming a lone pair. Our nucleophile was neutral. So the second step is a proton transfer because we had a neutral nucleophile. Now, again, how it's happening is a little bit different, but the reasoning is the same as what we've seen. So that oxygen is positively charged. We need to get rid of its extra hydrogen. But look at who's removing the hydrogen. We're using that carbonyl on the peroxy acid to remove that hydrogen. Here's where it gets weird. So the next step's the weird step. It's just even, it doesn't even get a special name. It's really just labeled as a rearrangement. There's a lot going on here. So we're going to just start up here at the top. So starting up here at the top, the lone pair on the oxygen becomes a new pi bond. So that is reforming the carbonyl. Fine. Good with that. Now we're going to take the R group. So look at how that R group is moving. We're starting from the electrons of that bond and we're moving onto that oxygen. Something has to move because when that new pi bond forms, if nothing moves, then that carbon would have 5 bonds. We know we can't have that. So the R group moves over. This is very similar to when we first started learning mechanisms and we learned about the 1,2 hydride and 1,2 methyl shift. So this is super similar to that. That carbon moves over and then we still have 2 more arrows. This arrow is showing that, it's really showing the loss of a leaving group. The bond between the 2 oxygens breaks and we're forming a new carbon-oxygen double bond. And then we're taking that other pi bond and creating a lone pair on our oxygen. So we do make a carboxylic acid. This is from the peroxy acid. It's very true. Yeah, peroxy acids are just kind of weird in general. I feel like they just kind of have like too much junk, and so they have enough wiggle room. They can do a lot of weird things. But we get that peroxy acid. We can get rid of that in our reaction pretty easily, though. In our workup step, if we had NaOH, that's going to neutralize that acid. It'll make it ionic. It'll make it water soluble. We can just wash it away in the water layer. And then the product we actually care about is our new ester. So I do know that that mechanism's a little weird and lots of little steps in the middle there. But are there any questions about hows or whys or what's going on? Okay. Then let's make sure we understand it. So we have 2 starting materials. We have our aldehyde at the top reacting with MCPBA, our peroxy acid. And we have a ketone reacting with our peroxy acid. So what are we going to make?
Carboxylic acid?
We are going to make a carboxylic acid. So our aldehyde is going to become a carboxylic acid. We're going to insert that oxygen right next to the hydrogen. And then on our ketone, are we going to put the oxygen on the left side or the right side?
Right.
Good, thank you. I don't think I left any carbons out. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah. Ester, and we put the oxygen right here because the right side was a secondary carbon, the left side was a primary. Secondary wins over a primary. Both of these reactions definitely lead us to our next chapter. So our next chapter is how to react carboxylic acids, esters, and even the reaction a couple prior to this where we talked about how to add on a cyano group. We have an entire section just on cyano reactions as well. So these pair up nicely with our next chapter. Questions about either one of these? Okay. Oh, so will the next chapter take 2? Honestly, I don't know. So I know that's what we have in our schedule. It is quite a few slides. Let me see. I have my notes right here. I did post the actual PowerPoint today. It ended up being 58 slides. Now, part of that is because I leave some blank slides in there to draw on, and I have like my example slides, so stuff I would normally do on the whiteboard. But it is quite a bit. Yeah, it's only 2 chapters, so it's just 19 and 20. And then our last test is 21 and 22. I don't think it's going to take as long as we have it scheduled for. So we'll see what it takes us. The last section in this chapter is really the same last section we see in most of our chapters, is looking at the big picture, looking at multi-step syntheses. There's this map that's kind of written out on this slide, and it's in our chapter, but it's written out to say, we know how to start with an alkyne or an alkene or an alkane and convert between those. We know how to make a halide and an alcohol and a carbonyl. And now that we know how to make a carbonyl, we also know how to react it using all of the reactions from this chapter. A good approach for multi-step synthesis reactions is to look at the functional groups that you're starting with, that you're ending with, and figure out how to make the conversions just from functional group to functional group. So if you're starting with an aldehyde and you're asked to just turn it into an alkane, well, we know how to turn an aldehyde into a thioacetal, and we know how to reduce that to an alkane. So kind of having those functional group to functional group pathways in your head is really useful. One of the ways to do that is to create a reaction map. So if you have a whiteboard, or if you can get to Dollar Tree and buy like a big poster board and write out just generic, either the words or like drawings like this, alkene, alkyne, aldehyde, ketone, ester, carboxylic acid, just kind of write out all these different functional groups and then draw arrows between all of them to show, okay, if I'm in a ketone, how can I get to an alcohol? How can I get to an alkene? And it might end up being like you can't go directly, but you're like, okay, well, I know how to go from a ketone to an alcohol, and I know how to go from an alcohol to an alkene. It kind of gives you those little pathways, and it helps you learn the pathways and remember the pathways by doing it that way. It becomes crazy messy, especially after the next chapter, because there's so many functional groups and so many different ways to convert them. But I also think it's super useful. It actually, after next chapter, it becomes hard for me to write multi-step synthesis questions, because you will know how to convert so many different functional groups to so many others in just one step, that it's hard for me to force you to do a reaction that is multiple steps. So good for you if you have the reagents down. Challenging for me. Let's see. Oh, we are pretty much at time. Yeah, I think we're done. That was our last slide, wasn't it? Oh, okay. There's this slide too. I forgot about this one. So this one's just showing us the carbon skeleton changes. So these reactions are specifically pointed out because there's so few of them. We don't actually have a lot of reactions that create carbon-carbon bonds. Most of our reactions are focused on functional groups and heteroatoms. So we have the Grignard reaction, which we kind of talked about what it can add. We can add on lots of carbons, but primary and secondary carbons at the Grignard location work the best. When we use the cyano, it's only adding on one carbon, but it is creating a carbon-carbon bond. And then our Wittig reaction, we talked about the limitations with that, but we are creating an alkene. So we do still have two reactive carbons because they're both vinylic still. So that's also useful too, because that means it can continue into more reactions. We have a whole alkene chapter. Okay, I think that's it then. That is the last slide. All right. Questions about any of those multi-step synthesis pathways, or that's not really a good question to ask you guys, but any questions about anything today?
I have a question, Professor.
Yes.
So I had I was in SI today, and we were going over mechanisms that you didn't cover in class. And quite frankly, I was struggling on those questions. So my question is, if you didn't cover it in class, should we need to cover them on our own time. If that makes sense.
It does, but there's not a straightforward answer because it's going to depend on what the reaction is. So the reactions that follow that nucleophilic attack, add a bunch of protons here and there, those are the ones that you need to know. So, and I know that's not the best way to describe it. When I give you the study guide, so top of my list for next week is to write our test so I can get you a study guide. But the reactions that I'll star and I'll let you know will be the ones you need to know. So short answer is that yes, you do need to know some that I didn't talk about, like the thiols. You should be able to draw those mechanisms. They look exactly like the acetal ones, but we didn't show them in class, but you still need to know them. Let's see, we did draw that one. We didn't actually draw either one of these, but it looks exactly like this one. So you should be able to draw any of those primary based nitrogen ones. Oh, we did talk about the acetal. It's not on here anymore because I don't save the notations, but the acetal. Oh, and that gets us back to reaction number 1. So yes on the hydrate, yes on the acetal. Cyclic acetal is the exact same reaction as the acetal, so yes. Imine and oxime and hydrazone, yes on all of those. No on the enamine. We did talk about that one, but it's a little bit different than the others, so you don't need to know the enamine one. Or this one, the hydrazone one. So I don't even think we talked about that one, but you don't need to know the hydrazone one. This one we talked about the acetal reversal today, so you do need to know that one. You don't need to know the others though.
Okay.
I think that covers everybody then. No on this one. We talked about why on that one though. Yeah. Did I cover all of them?
Yes, you did.
Okay. Sorry, that turned into a very long answer, but I figured I could just go through them quick. Anything else before we sign off for the day? Okay, so you don't have anything due today because our test was last week. On the schedule is the chapter 19 worksheet. So work on that, work on the lab if you haven't finished it, work on your formal report. For those of you that came in a few minutes late, if you're still here, in case you weren't the ones that left early also, I will be out of town this weekend, headed to Big Bear. So if I don't text or email you back, it's because I have bad reception. So I'll get back to you on Monday. But I think that's all. So have a good weekend, you guys, and I'll see you Monday or in office hours. Thank you too.
Thank you.
Professor?
Yeah.
Will you be available during lab time right now or tomorrow?
I won't be on Zoom, but you can always email me or text me. I will be in office hours tomorrow, 1:30 to 3:30 on Zoom.
Got it. Thank you.
You're welcome.
All right, thanks, Professor. You have a good one.
You too.
Thanks. Bye-bye.
Any questions from you, Justin?
No, sorry.
That's okay.
I was trying to listen in on the call, but actually I'm trying to multitask. I'm getting dressed for a job interview today.
Oh, good luck.
Yeah, so we'll hope so. It's at the Orange Mining Company, if you've ever been up there.
Oh, I have been up there. Actually, I've never eaten up there or anything, but Sheila and I went for a drive one day and we were checking out wedding venues, and we actually drove up there and like just kind of walked into the restaurant without talking to anybody, just like walked around and looked at it as a potential wedding venue, and it's pretty. It's a really pretty view.
Oh, absolutely. Sometimes, yeah, I'll just go up there and not even go into the restaurant, but just abuse it for the sitting up on the hill and just watching the sunset. Pretty nice.
The other restaurant that's just a little farther down the road, I can't remember what it's called, but it's just a little higher up on the hill, a little fancier of a restaurant. I went to a wedding there about a year ago, so it was a very pretty setting up there. So nice place. All right, well, good luck at your interview.
Thank you. See you next week. Have a good weekend. Have a nice time at Big Bear.
I will. I'm looking forward to it. Okay, have a good weekend.